everyone, welcome again. So today's lesson is on industrial chemistry, and this series that we're going to start studying now is on saponification. So in the previous series we've looked at sodium hydroxide production and how we actually created this product called sodium hydroxide. And in this series we're going to see how sodium hydroxide is used to produce soap through the process of saponification. So first, in today's lesson we'll talk about making soap. So I'm sure we all use soap to shower, or we may use some kind of weird, those gels. But in general, soaps are all very similar in how they work. And in terms of producing it, we will need to know how they're produced in order to understand how they clean, or their cleaning action. So in this lesson we'll talk about how it's actually made. So saponification is the reaction of an ester and hydroxide ion to form soap. So another word for this process is transesterification. So we're going back in the opposite direction to esterification. So remembering in esterification we looked at sulfuric acid turning an acid and a alkanol into an ester. Well, now we're going the opposite way, so we're breaking an ester using sodium hydroxide, which is a base compared to sulfuric acid, and turning it into a sort of acid and a alkanol as well. So generally soap is a carboxylate anion, the conjugate base of a carboxylic or fatty acid. So what that means is that this is sort of this is an ester here, and the soap itself is actually this section, which is like a carboxylic acid minus the H+. So you can see it's a carboxylate group. And then we just add sodium to that, and that gives us the soap. Okay? And it's a carboxylic acid of a fatty acid. So we'll talk about what all these things are in a sec, but that's where we're going. An alkanol, or water, is also produced by the reaction. So an alkanol, the most common alkanol that's produced is glycerol. And again, we'll talk about what all these things are shortly. So the conditions and catalysts that we need for this reaction. So saponification can be described as the hydrolysis of an ester under alkaline conditions. It's very complicated, but essentially all it is that it's the addition of water, essentially, or hydroxyl ions to an ester under alkaline conditions. So the hydrolysis uses a zinc oxide catalyst to speed up the reaction. So if we have zinc oxide, we can speed up this reaction a little bit. And the reaction usually occurs more readily at high temperatures and pressures when the components are a little bit more energetic and more readily broken down. So the saponification process. So what we actually do is we take fats and oils and inject them into the high pressure chamber and react them with steam. So this produces glycerol, water, and fatty acids, which are good. And the fatty acids are combined with sodium hydroxide to make soap. Okay. Now, in order to get the correct composition, we need to understand what the effects of the composition is. So if there's too much fat, the soap will feel greasy and won't foam as well. And if there's too much sodium hydroxide, it will be caustic and irritate the skin. So if there's a little too much sodium hydroxide, what you feel is that dryness that a lot of people associate with soap. And it's why a lot of people don't use soap for cleaning purposes. They prefer to use, say, like a shower gel or something that doesn't dry out their skin as much. And the reason why it dries out your skin is because there's too much sodium hydroxide. Okay? So care must be taken to ensure the right amounts of each reactant are added. Otherwise you get these bad batches of soap. So what is the actual components of soap? Well, there's fat, essentially, which is an ester, and then there's sodium hydroxide, and those are the only two things that we need. So what kind of fats are there? Well, there's saturated fats, and for those who study maybe PE or biology, these saturated fats are fatty acids that, so fatty acids can come in saturated or unsaturated molecules, and saturated fatty acids contain only single carbon-to-carbon bonds. So in other words, they're like alkane groups, and it means that they have the maximum number of hydrogen because each carbon can bond to the most hydrogen possible, And so we call them saturated essentially with hydrogen atoms. That's why they're called saturated. So they're saturated because they have the maximum number of hydrogen atoms that they can. And saturated fatty acids are usually found in animal fats, and they're very energetic. So if you burn them, they produce a lot of energy. There's unsaturated fats as well, and these contain double or triple bonds, similar to saturated hydrocarbons and unsaturated hydrocarbons. So obviously, because of the double bond, they contain fewer than the maximum number of hydrogen atoms. And they're usually plant oils, so like vegetable oil or palm oil or coconut oil. These are unsaturated fatty acids. So some various types of fatty acids that you might see is palmitic acid or palm oil. So it's essentially just an acid group with 15 carbons before the carboxylic acid group. There's fatty acids, the stearic acid, which is animal fat. There's 18 carbons in total. Unsaturated fatty acids, which could be oleic acid in olive oil. So there's essentially this section here, which is the nonane group before the double bond, and then you get another 8 carbons after. So you don't need to remember all of these. This is just for completeness, but you will be able to see some of them used later on. And linoleic acid, which is in many plant oils. It's a very complex molecule, okay? So you don't have to worry too much about remembering all these, but just be aware that they exist, and that's all you need. Okay, so now we're going to talk about glycerol. So many fats and oils are triesters of glycerol and fatty acids, okay? So glycerol is this molecule here, and glycerol's IUPAC name is 1,2,3-propan-triol. So you can see propanol, or propan, is here, 1, 2, 3, prop. So ol usually means there's a hydroxyl group. So there's, in this case, 3 of them. So you get triol and 1, 2, 3, propan-triol, okay? And that's the IUPAC name. And in triglyceride, in a triglyceride such as stearin, which is this molecule, or glycerol tristearate, each hydroxyl group is replaced by the conjugate base of a fatty acid, okay? So you can see this is the glycerol group at the top, but what we had was OHs, but now they're replaced by this O. And this whole section here is actually just the conjugate base of a very long fatty acid. And so that's why it's an ester. You can see that this is an alkanol, and then this is an acid. And so an alkanol and an acid combined gives you an ester. So this is a very big ester, which we call stearin, or glycerol tristearate, okay? Where this is the stearate molecule, and this is the glycerol molecule. So now we'll talk about the actual transesterification process and what actually happens to produce soap. So this is our triglyceride, or our stearin, which is our fatty acid. So this is our fat that we've taken. So we've found this fat somewhere, and we want to turn it into soap. And this whole thing is it. We happen to have some very concentrated sodium hydroxide, not sodium chloride, and we've got, now we're going to react them together, okay, in a high pressure, high temperature environment, okay? So what happens is this Na and OH break up, and you get 3 Na ions and 3 OH minus ions, and then the bonds that were here are all broken, right, because of the heat. So, and also the presence of these ions here. So you get a negative charge on the end of each of these stearate molecules, or stearate ions, and you get a positive charge, obviously, because they've lost the electrons that would have gone there, okay? So we've broken the bond here. Then, those 3 NAs you can see joined up to the end of these stearate molecules to form sodium stearate. So 3 of them, 1, 2, 3. And the OHs join the negative end of these to form this glycerol group. So this whole thing is glycerol, okay? So to remember that process, we started with triglyceride, and then we broke it up and then added OHs to the top section, and then to these long stearate chains we added 3 Na+. And these 3 molecules are our actual soap molecules, and this glycerol is used for other purposes later. Okay? So that's the actual transesterification process. Now that soap structure that we saw is a mixture of a soluble salt of long chain fatty acids. Okay? Sodium stearate, for example, consists of stearic acid with its acid proton replaced by a sodium ion. Okay? So this squiggly line here represents the stearate chain, and this would have been stuck to there. So when you put it in water, this dissolves and goes away, leaving a negative charge here, a negative head on the end of a stearate chain. So this is the molecule that we saw before. CH3, CH2 times 16, COONA. So this is our sodium stearate molecule. So soft soap and hard soap. Hard soap are usually made from saturated animal fats, whereas soft soaps are usually made of unsaturated plant oils. Now by blending different fats and oils, soaps of different qualities can be made, and that's how soap is generally produced. Okay? So that wraps up today's lesson on making soap. It's just a general overview of how soap is made. So we take a triglyceride, we break it into glycerol, and then stearate, and then the stearate is bonded with sodium to form sodium stearate, which is our soap. Okay? So move on to the question segment. So first, name these compounds. This is a very, very difficult one to name, but hopefully you can do it. So it should seem familiar because there's a 16 here, which is strange, and there's 3 of them, and a CH3. So you can see that this is similar to our glycerol at the top, and this is similar to our stearate, so it's very likely that we already know what the answer is. So this is called stearin, or glycerol tristearate. Okay? It's just a rejig of what we saw before. So if you could see what was going on, then that would have been easy. If not, that would have been much, much more difficult for you. Okay, so this one. You've got CH3, C16, COOH. So it looks like this one, the stearate molecule, so it's probably stearic acid. Stearic acid is correct. Or you can say it's octadecanoic acid. So you've got 16, that's hexadeca, so 6, 10, so 16. And you've got 2 more carbons. So 16 plus 2 is 18, so that would be octadeca. So you can see octadeca. It's a alkanoic acid, so it would be octadecanoic, and it's acid at the end. So that's how you would have named that. Or you could just call it stearic acid if you can remember that. And lastly, this one. Well, it looks like this one, but it's got, instead of having a H, it's got a K+. So if you take the H out of, say, ethanoic acid, it becomes the ethanoate ion. So if we take the H out of a stearic acid, then it becomes the stearate ion. And then we just put whatever's here at the front. So it would be potassium stearate. And there you go. Alternatively, you can call it potassium octadecanoate. So potassium octadecanoate. Okay. Question 2. So the saponification of glycerol trioleate by potassium hydroxide solution produces glycerol and a soap. Write a balanced equation to show this reaction and name the soap. Okay. So this one here. So this one here is the trioleate. So if you look back through the previous parts of this lesson, you'll see that we named what trioleate or what oleate was. And this part here is the glycerol. So that's why it's called glycerol trioleate. And it takes 3 potassium hydroxides, which is here. And that forms the glycerol, which is here. And this 3 potassium oleate group, which is at the end here. Okay? Very complex molecules. We're not expecting you to be able to name every single possible branch of them, but you should be able to see, if given the names, how you would approach them. Okay. So write an equation to show the saponification of this ester by sodium hydroxide. So here's our ester. It's a generalized ester. So if we add NaOH, we get this section minus this R prime, and we get, so this is our soap, and then this R prime gets combined with the OH to give you some kind of alkanoic acid, alkynyl group. So ester plus NaOH gives you soap, or in this case sodium alkanoate, and some kind of alcohol. Okay. So the name of stearic acid comes from the Greek word ster, meaning tallow, the fat of a cattle. So tallow is another word for fat. Why was this name chosen for this substance? Well, stearic acid is named after stearin, which is glycerol tristearate, which is a type of animal fat. And this type of fat was first refined from tallow, so it would be appropriate to name the fat after the tallow, hence the word stearin. So because we refined it originally from tallow, which is animal fat, it makes sense to call it stearin because it comes from the word meaning tallow. Okay. So that wraps up today's lesson on making soap. So we've gone through the general process of making soap, and in future lessons we'll be talking about what industry does to actually make the soap. What are the processes when we make soap? So we'll look at how we optimize the soap making process. So I look forward to seeing you at our next lesson.